Good morning. Welcome to the IP Showcase. Our presentation is from Simon Rankine, talking about API security. Now, this is an extremely important topic, particularly when we look at large-scale deployment. We need a way to protect the interfaces that basically give access to all the features and functions in our ST2110 devices. We need a way to make sure that those APIs are secure, and that's what Simon's going to be talking with us about today. So without further ado, thanks, Simon.
Thank you very much. So as Wes said, my name's Simon Rankine, and I'm a research engineer at BBC Research and Development. But perhaps more importantly for this morning, I'm also a member of the AMWA NMOS API security group, and we've been looking at ways to add security to the NMOS APIs, so starting with ISO 4 and ISO 5. So why do we want to do this? After all, you could say that, okay, I'm going to run my APIs in an isolated network behind a firewall. Surely that's good enough. Well, first of all, we want to be able to run the APIs in networks that aren't necessarily like that. We want to be able to run them maybe on the internet or on client networks, or maybe if we're in a particular like stadium or something, we need to run it on that kind of network. So there are circumstances where we're not able to use an isolated network. But it may be that if we're somewhere particularly sensitive, that's insufficient. Even if we have an isolated network, attackers can still get in using, for example, USB sticks. That's quite a common attack. So having an isolated network isn't always sufficient. We know that broadcasters are a target. The TV5 Monday attacks, which took the entire station off air, demonstrated that hackers are looking to attack broadcasters. And there are a lot of people out there who don't necessarily agree with everything broadcasters are saying. So we need to be vigilant, and we need to be protecting ourselves against malicious attacks on our infrastructure. Finally, security gives us an extra bonus. It doesn't just protect us against deliberate attacks on our networks, it also protects us against accidental misuse of our facilities as well. So the thing about the NMOS APIs, they're built on HTTP, this standard web technology that's used to serve every web page in the world. And from that point of view, the NMOS APIs have always been securable. There's not been anything stopping manufacturers putting security in front of the APIs other than that it has the potential to break the interoperability. So what this work is about is defining a common way of implementing security across the APIs, across vendors, so we can ensure that we maintain the interoperability that's at the heart of NMOS. On top of that, the work we're doing is about ensuring that when we do this, that we do it in the best way possible. We achieve the best level of security with the APIs and set down some good practices. When we talk about security, what do we really mean? So there's a few sort of key principles that we're looking for here. The first is confidentiality. This idea that when our API client is connecting to an API server, say a broadcast control system to a camera, we don't want anyone else on the network to be able to read the interaction that goes on between those two devices. The information that's carried in the NMOS APIs, particularly when we look at ISO 4, tells an attacker an awful lot about our facility, and they can use that information to carry out further attacks. Then we need identification, because it's all very well and good having confidentiality between client and server, but if the client is talking to a server that is actually a malicious attacker, then the confidentiality is completely pointless. So we need to be able to assure our client that it's actually talking to a trustworthy server. Integrity, we need to be able to check that as data is moving around the network, that it can't be tampered with in any way. So if you think about an ISO 5 routing request, if someone was able to tamper with that as it moved around the network, they could potentially change the way a routing request is carried out and interfere with operations. Authentication. So similarly, a client needs to be certain that information it's receiving from the server is actually coming from that server and hasn't been injected into the network somewhere else. And finally, authorization. APIs need to be certain that what the client is asking them to do, that particular client is allowed to do. So take a multi-studio environment. Maybe all our studio facilities are connected to the same management network, but we don't want the the team in Studio 1 to be able to control resources in Studio 2 because that's not their studio. So we need a way of being able to arrange that kind of authorization. From a technical point of view, we broke the work down into 3 different research areas. So connection security. This was about making sure we've got that confidentiality and sort of not being able to interfere with things. And for that, we're using TLS over HTTP. So this is exactly the same protocol that's used to secure interactions over the internet. You'll have seen the green padlock in the browser. That means that you're using TLS under the hood. Establishing trust. So this being able to check that the server you're talking to is the server that you think it is, and how we arrange for that to happen in the broadcast facility. And finally, client authorization, so this business of being able to check that clients are authorized to undertake the actions that they're asking to do. And we've approached that problem by using OAuth 2 with JSON Web Tokens, which if you've ever kind of come across, say, your social network wants to access the photos held on a photo sharing cloud storage service, it will pop up a little box and say, hey, is this social network allowed to access your photos, say, and you click OK. Under the hood, that's using the same technology as we're using here. So we can kind of think about this in a layered way. This authorization stuff, that sits at the top because that's kind of application layer. It needs to understand about how a broadcast facility works. I'm not going to go into that in too much detail, but Arna from Riedel is going to carry on with that story at 10 o'clock straight after me. I'm going to focus in a bit more on the transport security. So this is talking a little bit more about that TLS and how we secure the communications and how we establish trust. There's kind of stuff that sits below this. So we've got network security, making sure our switches are configured securely, that devices have correct software updates, things like that. Clearly, that's important, but it's out of scope for the API security group. And beneath that, you've got things like physical security. Who has access to apps rooms? Can people plug stuff into our devices that shouldn't be able to? Again, important, but out of scope for this particular piece of work. So let's talk a little bit more about connection security. The way we do this is we take our normal HTTP, which is, if you look at it in something like Wireshark, you can see exactly what's going on. But we pass it through TLS, we tunnel it through TLS, and that encrypts the traffic. TLS, as I said, is incredibly widely used. If you log onto your internet banking or a social network or whatever it is, if you see that green padlock in your browser, you are using TLS. Okay? TLS is made up of a collection of different algorithms, as we'll see in a moment, and together those algorithms form what we call a Cipher Suite. TLS supports a wide number of different Cipher Suites. Some of them are secure, some of them not so much. And so part of this work has been to determine which Cipher Suites we should be using with NMOS. So let's dig into a little bit more about what happens when you make that first connection with a TLS secured endpoint. First of all, the client gets hold of the server and it says, hey, I'm here, I want to talk TLS with you, and I support these versions of TLS, and I support these Cipher Suites. The server gets back to you and says, okay, I want to use this version of TLS, and I want to use this particular Cipher Suite. It also passes back to you a certificate that belongs to the server. That has a few different things on, but crucially, it has the public key of the server, and it has a signature on it that verifies that that server is who it says it is, and I'll explain how that works in a little bit. Finally, it passes across a random number, and that random number is quite important because it's used as part of a process in the client to generate a secret. And that secret forms the basis of the secure connection between the client and the server, because we need to use symmetric encryption to be able to communicate, because symmetric encryption is a lot less computationally resource intensive than the asymmetric encryption we're using to set up this connection. In order for that secret to pass from the client to the server, we do use asymmetric encryption. We take the public key from the server, use that to encrypt the secret that the client has generated, and we send it back to the server. And the important thing is here that once that secret has been encrypted with the public key from the server, only the server's private key, which it's kept to itself, can be used to decrypt it. So at this point, we have a secret at the client and at the server that only those two know, and no one in between could have stolen. And at that point, we can use our symmetric encryption to carry on the conversation, and off we go, and we have a secure connection. So in order to do this, a number of different algorithms are used under the hood, and I mentioned before these form a Cipher Suite, and this is what a Cipher Suite looks like when it's written down. So this forms multiple chunks, as you can see. The first chunk is the protocol we're using, TLS. You're unlikely to see anything else there these days. The second is the key exchange cipher. So this is the algorithm that's doing that back and forwards to establish the shared secret. There's a few of these different ones, and some of them aren't considered secure anymore. Next is the key authentication algorithm. That's used to check that the certificate provided by the server is legitimate and is signed by a party that we trust. Next is the block cipher, and that's the cipher that's used to encrypt traffic after the shared secret has been established. As the name suggests, it encrypts a discrete block of data, which obviously when we're trying to transfer an arbitrary sized piece of data like a web page isn't very useful. So we need a block cipher mode, also called a streaming cipher, to be able to chain those blocks together in a secure way so that repeating patterns can't be spotted in the data, for example. The last part of the Cipher Suite is the hashing algorithm. That's not responsible for any particular step in this, but is used in a variety of different ways in the TLS protocol for performing checksums and things like that. So this is the list of Cipher Suites that we've selected for use with NMOS. That's based on a lot of research into the current best practices from different bodies in the IT industry that provide recommendations on this sort of thing, and research into sort of how the underlying algorithms work and whether they're likely to have good longevity. In particular, I'd like to point out this one at the bottom. This one is a kind of slightly lighter weight to implement version, so it's used a lot in Internet of Things devices because it's less resource intensive for embedded devices to be able to operate with. You may have heard of this technology referred to as SSL. That's a little bit of a misnomer, so I've been a little bit careful with my language not to call it SSL, because actually all three versions of SSL are now insecure. TLS 1.0 itself is actually considered insecure as well, so really you would only hope to see TLS 1.1 and above. TLS 1.1 is similar to TLS 1.2, but 1.2 has a few extra options in it, so the majority of web pages you'll see these days is served with TLS 1.2. TLS 1.3 has recently been published. It's starting to find its way into implementations now, but it's still not really out there. But we've also got provision in BCP 00301 for use of that protocol because it will become best practice in the near future. So I mentioned earlier we have this process of checking the certificate that comes from the server to ensure we trust it. Now, how is that trust established? The certificate has a signature, a cryptographic signature from a certificate authority. That certificate authority is typically a third party. You may have heard of organizations like DigiCert or VeriSign or Symantec. There's hundreds of them. And they are able to sign certificates to verify that you own the domain that is on that certificate. And also many companies operate their own certificate authorities internally for use on their intranet and so on. Certificate authorities make their public keys available to browser manufacturers and operating system vendors who will audit them for security, and if they're happy with them, they will distribute the public keys that correspond to those certificate authorities in browsers in operating systems. And it's those public keys that are in your browser that allow your browser to check the signature that the CA has put in the certificate provided by the server so that you can verify that that certificate is genuine. So this is a little bit how the setup looks. You've got your CA up here, and it issues and signs the certificate that goes on your server that's then presented to your client when the connection is established. Meanwhile, the corresponding public key to the private key used for the signing is issued by browsers and operating system manufacturers. We have a similar setup in the demo over there. This is a little bit more detailed, but in order to do the demo here, just on the stand over there, I've used OpenSSL to set up a CA just for us. It's not generally publicly trusted, but I've installed the public key from that CA into the NUC that's running the demo over there so that it trusts it. I've used an intermediate CA, your root CA. Generally, the secret key for that is only brought out for special occasions because we need to keep it super secure. So we have an intermediate CA that is actually used for the day-to-day signing of certificates. We also have what's called an OCSP server. That's used to allow for certificate revocation checks. And we attach the result of that check to the certificate when it's provided by the server. And again, that's signed by the CA, so the server can't fake the result of that check. We have a Python Flask instance that's serving our ISO 5, proxied through an Apache server that's dealing with the TLS termination for us, so we don't need to worry about it in our actual ISO 5 implementation. That then makes the connection to our client. The client has the CA public certificate installed on it, and it trusts the web page. And the result here is, you can see, I get my green padlock, and you can see it's, the certificate is issued by an AMWA CA that I set up, and in the background you've got the ISO 4 registry. So this is ISO 4 being served over HTTPS, all nice and secure. So all this is codified in BCP 00301. That's available on GitHub if you want to read more into it. I've also published 2 white papers on this, the first of which is around how the Cipher Suites were selected for BCP 00301, and the second of which is going into a lot more detail about how the trust and authentication and certificate authorities could be used in a broadcast environment, and how we can go about distributing those certificates. So yeah, that's everything I got. I think I've got time for some questions.
Yes, we do. Does anybody have any questions for Simon?
So the certificate is issued based on the URL, correct?
Yeah, so that's what's used as the point of trust. Yeah.
So in NMOS right now we're using IP address. Is this
Yep.
no URL? So does that mean that we're going to have to update that as well as part of doing the security?
That's part of the best practice, yeah.
Oh.
You can issue certificates based on IP addresses, but it's generally considered bad practice, because obviously if you change the IP address that a device is running on, or you're doing some kind of load balancing, you then have trouble with the certificate because you need to update it. So usually we use DNS names in certificates.
Okay, thank you very much, Simon.
Cool. Thank you.
Appreciate it.